Problem 5 is the same setup as problem 4. Part A asks us to identify which of the above vectors represents the net force exerted on the sphere at the moment shown. So we know that the ball is being kept in a circle. So that's a centripetal force. So we know that the net force is towards the center of that circle. So the answer is A. You may get, yes, there's gravity acting down and there's tension in the string L, which is a second quadrant vector there. But the net force, okay, exerted on the sphere at that point is towards the center of the circle, which is towards the left. So 1 point for getting A and 1 point for indicating that the net force is towards the center since it's moving in a circle. Okay, part B asks, is the magnitude of the tension in the string greater than, equal to, or less than the weight of the sphere? So even without drawing a free body diagram, we should be able to tell that the tension is actually greater than the weight. But let me draw the diagram just anyways. Here's mg acting down again, that's the weight. Here's tension acting up, and I'm drawing at the point that's shown in the illustration there. So we know that there's no acceleration in the y direction. So that means that the y component of the tension is balancing out gravity. So we know that the y component of tension is equal to the weight, and we know that the y component by definition is less than the actual vector, right? The components are always smaller than the magnitudes of the vector, so we can use our reasoning to say that. So 3 points for that question. 1 for saying that the tension is greater than the weight, 1 for explaining that it's the y component, for making some argument that you have to break up the tension into components to solve this, and then a justification that since the y component equals the weight, then the actual vector has to be, the magnitude of the whole vector has to be greater. So 3 points there for part B. Part C says the string can never be completely horizontal no matter how fast the platform is rotating. Without writing any equations or formulas, explain why. Okay, so the answer is there always has to be a y component because you've got to balance gravity. If the object is going to spin in a horizontal circle, something has to balance gravity. So there has to be a y component. So that angle that the string makes with the vertical can never be 0. Okay, so it can never be completely horizontal. So that's the answer to part C. Okay, so 1 point for identifying that the vertical component of the tension has to balance gravity, and then 1 point for saying that since that can never be 0, the angle can never be a right angle there. So that's part C. 2 points for that. Oops. Now for part D, we have 2 equations. One of the following 2 equations for the square of the tangential speed as a function of theta is consistent with our statement in C. So we're going to indicate which one that is. And the answer to part D here is that, this is number 1 and this is number 2, is that number 1 is consistent with part C. And here's why. First of all, as theta approaches 90 degrees here, the cosine of theta is 0. So this equation is going to blow up, right? As theta approaches 90, which is what we have said. We've said that theta can't get to 90, right? What we also see is that theta increases, the velocity is going to increase because the sine is increasing and the cosine is decreasing as we go through this quadrant here. So 2 things there. It shows that no matter how large velocity gets, theta will never get to 90 degrees. That's consistent with what we had decided before. Now, the problem with equation 2 here is that if theta is equal to 90 degrees, I get an answer for V, right? V equals 0 because the cosine of 90 degrees is 0. So equation 2 can't be consistent there. Now I'm trying to remember if you had to do both of those, yeah, you had to show which is consistent and why the other one is not consistent. So you did have to have actually both of those parts to get these points. So 1 point, it says the rubric for addressing the functional dependence of either equation. 1 point for showing that as theta goes to 90 degrees, the velocity increases in equation 1, and then 1 for pointing out the flaw in part 2. So I guess you could have shown that the first one was correct and not explain that and only missed out on 1 point of that. Okay, so let's move on to part E. So in part E, we are again trying to make an experiment to find acceleration due to gravity. And the procedure here says that we change the length of the string and then adjust the velocity so that the angle stays constant. So again, looking at the functional dependence here, we want to graph v squared versus L. Okay, we could also graph v versus rad L. It doesn't matter. But we want to put v on the y-axis and L on the x-axis, or v squared versus L and v versus rad L. And then we have to have, again, the correct power relationship. So not v versus L and not v versus L squared, but we've got to have v at a higher power, one higher power, I guess, if you will, than L. And then, again, they don't ask us what the slope would be, okay? If we graphed v squared versus L, then the slope would be g sine squared theta over cosine theta, and then obviously you could just divide out the theta stuff and find g. But again, they're not asking us to do that, but it is what we could do. So then for part F, they're going to actually throw another angular momentum question in there. Let I be the rotational inertia of the sphere rod platform system about a vertical axis through the center of the support rod. Does I increase, decrease, or stay the same when L increases but theta stays constant? So we're going to have a longer string here, the same answer, or excuse me, the same angle, which really means that the mass is getting farther from the center. And I hope that we learned in that unit that if the mass is further from the center, then I is going to increase. Right, so 2 points for that. 1 for saying that it increases, and 1 for realizing that with a longer string in the same angle, the mass is going to get further from the center, which is going to increase the moment of inertia. So that's 8-5.